This is a brief tutorial example on how to use Simulink to solve a problem with a dual gravity drain tank system. Okay, so we have a model that we have set up with a liquid level in a first tank and also a liquid level in a second tank. And then we also have a pump from a reservoir. Okay, so here's a reservoir that the second tank is draining into, and then we have a flow going into the very first tank that will then start to drain into the second tank. And so we're trying to maintain a level. Okay, so we're going to be designing a level controller that is going to be adjusting our pump flow rate to maintain this second level. And we also have a valve here as well where the water can flow directly into the second tank. We're not going to use that for this example. We're just going to use the water flowing into the first tank. Okay, so what we need to do is first of all go to the APMonitor.com website. We're going to go down to the process control course and go ahead and select that, and then we're going to select homework here on the right. Okay, so homework, and we're going to be covering special problem number 3. Okay, so here's the problem statement. So we're first of all going to fit a first order plus dead time model to dynamic data and then tune a PID controller. Okay, and then we're going to use Excel to give us that FOPDT model, and we're going to create a doublet test and then tune it with ITA or IMC controllers. Okay, so I'm going to go back and just download the example files. Okay, so this is a Excel and Simulink files. I'll just go ahead and save it to the desktop. Okay, and I'm going to go close out of that. The first thing you need to do is extract the files. If you don't do that, it won't run properly. What I'll do first of all is just go ahead and go into this 2-tank Simulink, and this is the Simulink file right here. So what I want to do is just go ahead and open that, and that will open up MATLAB, and then from MATLAB it'll open up Simulink. Okay, so what we're going to do is we're going to adjust the pump flow rate to try to maintain level. We need to first of all obtain a model that allows us to understand the relationship between the pump flow rate and the second level. Okay, so we're going to develop a dynamic model, an empirically based dynamic model to do that. Okay, and so here's our Simulink model. I'm just going to hit plus a couple times, or just to zoom in on this. Okay, and then okay, so I've got my system. Now this doesn't look too much like a tank. Okay, but here's the tank right here, the dynamic model of the tank, and then all of the rest of this is just output. Okay, to be able to measure or see the levels. Here's where I can adjust the pump output, and here's where I can adjust the valve position. I don't want to change this right now for this simulation, and when we design the controller we'll also have a level set point as well. So first of all, I just want to do some step tests, or double it, or pulse response, or else a PRBS on this pump output to be able to see what it does to the measured level. Okay, so this is going to go between 0 and 1, and I've got my simulation time here. And then what I need to do is go ahead and run, click the green button here to go ahead and run this simulation. Okay, and when I do that, when I click run, it's going to bring up a okay, it's going to go ahead and compile it, and then it's going to go ahead and start running. So you see no level at this point, and then what I'm going to do is go ahead and open up this pump output, and let me go ahead and just minimize that. And I'm going to set the pump output to 0.5. Okay, and when I do that, let's see if I've got any. Let's see if this is running, or if I did something wrong. Okay, so it looks like I paused it. Okay, let me go ahead and click continue, and go back to my diagram here, and you can see that the tank is starting to fill up. Now, first one fills up faster than the second one because all of the liquid is coming into this top, okay, and then draining down into the second tank. And then what I want to do is maybe let me go ahead and just minimize this and move it over. Now I want to change my pump output to maybe I can use the slider, or I can use this text box. Okay, so let me just go ahead and increase it a little bit. Okay, and you'll see it start to increase a little bit more in terms of level, and then I don't want to overfill the top tank, and then I'll go ahead and decrease this one. Okay, and you can see the response as this is draining out, it's draining into tank 2. Tank 2 is continuing to rise, and now it's going to start falling. Okay, so you can see this running, it's 50% of the way done. Okay, and if you want to terminate it at any time, you can. I'm just going to go ahead and terminate it with this data like it is, and when I click stop, it'll bring up a plot that shows the pump output, the level, and then the level 2 and the level 2 set point. Okay, actually this is labeled incorrectly. This is actually level 2, and the blue line is level 2 set point. Okay, so I'm going to go ahead and close this now. Okay, so we have all of the data that we need to fit a first order plus dead time model. And let me go ahead and minimize this. One of the things that you saw from the Simulink diagram, let me just go ahead and make this bigger again. We had the data output to this data manual.mat, okay, and then also at the very end it read this in and then also put it out as data underbar manual.txt. Okay, so two things that it output, and we're going to go ahead and just retrieve the data manual.txt, and if I open that up, I'll see a number of columns of data, and in the first one you can see that I had time right here, and then this is my this is the percent or the percent pump. Okay, so I changed that from 0.5, and then you can see. Okay, actually that is not the pump. That is the set point right there. This is the valve, and then this one right here is the pump, the fourth column. This is the liquid level in tank 1 and liquid level in tank 2. Okay, so let me go in, and I'm just going to copy this file. Okay, just Control C. And I'm going to come over here to fit first order plus dead time in Excel. And if I open this up, this is a worksheet that's been created to help you fit a first order plus dead time. So let me just go through this briefly. I have my three constants for a first order plus dead time. I have my gain, my tau or time constant, and then theta, which is my time delay. And then I need to insert these values from my data. I need to put in my time, I need to put in my manipulated variable or controller output, or also the input to my system. Okay, and then I need to also put in the measured output, okay, or the controlled variable, the thing that I'm trying to eventually going to try to maintain with a controller. Okay, I don't necessarily want to change these columns right here, just copy them down to match the number of measurements, and I'll be able to see my fit here, and also my manipulated variable below it as well. Okay, so that's my data. What I'm going to do is just go ahead and insert my data here. You can either do it into a new sheet, or you can just copy it in. Okay, I'm just going to go ahead and copy it in here, and then I'm going to do data text columns, and I'm going to say it's fixed width, and it correctly identified the different columns for me. Okay, and so I have my data here. And the first thing I want to do is put in my time. So I'm going to do Control Shift down, and just grab my time, and then put it over into my time area. I'll make that just a little wider so I can see it. And then let me go grab my input. Now this is going to be my pump. Okay, so that's going to be the column of pump values is my input. Okay, and then my measured value as well. Okay, so that's going to be my second tank. I want to get a description, dynamic model description to my second tank. So this is the third one that I need to put in to my system. Okay, so the other thing I need to do is now just go ahead and trim some of these for the ones that need to be. Okay, so right here is where I just need to delete these rows because that was from the old data that was provided with the example. And okay, so I've gotten rid of those. Just have the data that was from the data that I wanted to read in. Okay, so you can see that the fit is pretty terrible right now. Okay, so not very good agreement. But you see the 0.5 initially went up to 0.7 something and then back down to a lower value on the manipulated variable, a little bit under 0.2. And we're going to try to fit it by changing these three values. So I'm just going to open up Excel Solver. So let's see. I need to do, if I don't have Solver in here, I need to come over to File, and I always forget how to do this, so hopefully I can do this on the fly here. I think it's Add-ins, okay, and I do Solver Add-in and OK. Okay, and then let's see if that came up with Solver Add-in. It did not. Let me try that again. Options, okay, add-ins. I think I need to do something. Excel add-ins, Solver add-ins, go. Okay, and then I need to click Solver add-in there. Okay, now I should see Solver over on the right. Okay, now that Solver is there, what I want to do is set my objective. I can select either of these, either the sum of squared errors or the sum of absolute errors. Okay, I'll go ahead and select sum of squared errors. And then I'm going to try to minimize that by changing these three cells here. Okay, I'll just select those three cells, the values. I also had some constraints set up as well. I just said that theta and tau have to be greater than 0. Also tau just greater than a very small time constant. Sometimes that helps the solver if you avoid getting stuck at 0. Okay, and I'm going to go ahead and keep the solver solution. Okay, so sometimes it doesn't change this with solver. Sometimes it does work well. Sometimes I find that I need to manually fit this theta and then optimize these two. In this case it did an okay job of fitting. You can see the red line, which is the model, versus the black, which is the measured. Okay, so I have my time constant and my gain and my theta. Okay, so I'm going to take those and let me go ahead and just paste those into a new notepad, for example. Okay, and one thing that I can do with just initial tuning values, this is just a back of the envelope. If you don't want to use IMC or ITAE, I'm just going to say that my K sub C is going to be approximately, this is for my PID controller, I'm just going to say it's approximately 1 divided by the K sub P, and then my tau I is going to be approximately equal to my tau P, which is equal to the 97.32. Okay, and then this is just my theta P here, and for my third parameter, my tau D for a PID tuning, initially I'm just going to say 0 for the derivative action. Okay, so let me go ahead and put this back into Simulink, and let's just see what kind of values we get for our controller tuning here. Okay, so I'm going to cancel, I'm going to hold on to that, and let me just go back into the Simulink. Okay, so now I want to set up and have a PID controller adjust the pump output instead of myself. Okay, so I'm going to come over to View, and I'll do Library Browser, and that will bring up a list of different things I can insert into this. Okay, so I'm going to do a PID controller, and then I'm going to drag that PID controller down into my Simulink model, and now I want to have a PID controller that is going to be able to operate on this pump. Okay, so now instead of me controlling the pump, I'm going to delete that. Okay, so I'm no longer going to be controlling the pump. Okay, but we're going to have the controller do that for us. So the thing that we need to input into the PID controller is an error. So here's our set point, for example, and our measured value for the height in the tank is that is going to be right here. Okay, so the height going out of the system and into this plot here or the plot of the tanks, we're just going to drag this value off. But the other thing that we need before we do that is we just need to compare it with the set point. So I'm going to put a sum in there as well. Okay, so we go ahead and drag the sum into this block, and we're going to compare the set point. So I'm going to right click right here next to this level set point. If you right click, it'll bring a signal off. You'll see a little dot there. It'll just duplicate that signal and bring it off. Now you'll see a plus and a plus here. I wanted to actually do a plus and a minus. I want to be comparing these. So a list of signs, I'm just going to change that to a negative and click OK. And so I'll see a plus and a minus there. And I also want to right click. I'll just right click right down here, and that will allow me to bring off this signal for the height. Okay, and then that is going to go into my PID controller. So that's an error that's coming in, the difference between the set point and the PV. And then out of that is going to come the signal to maintain my pump. Now I'm also going to, I had a plot set up as well for view pump. I'm just going to feed that back in now. Okay, so this is going to be controlling my pump. I want to put in some of those initial tuning values that I had. My proportional, let me go back to my sheet here. I'm just going to put in the inverse of the case of P, and that's going to be my just initial guess on my proportional term. And then integral, the integral in PID, for this controller tuning. Let me just go ahead and write this in one note. So if I have KC, tau I, and tau D in Simulink, the built-in PID controllers, the P is going to equal KC, the I term is going to be KC over tau I, and the derivative term equals KC times tau D. Okay, so I just need to translate these into P, I, and D. Okay, so I've got KC. I've already put that in. Now I just want to put in this value, and this value was going to be 0. So I just want to put KC divided by tau I. Okay, so I'm going to put in my KC right at the, okay, so that's KC value just like I had above. Okay, and then I'm going to divide by, I think it was 97. Let me check that out. Okay, so it's 97.3 for my tau I. Okay, so this is just an initial guess for the PID. And let me go over to PID Advanced. I want to limit the output. My upper saturation limit is 0, or sorry, is 1, and my lower is going to be 0. Okay, so that's just going to clip it. It's going to say that the pump can't go above or below that value. And I have my anti-windup method. I'm just going to go clamping on that. So it'll clamp the output and stop winding up the integral term if I reach a saturation limit on the output. Okay, so here I've got my PID controller, and let's just go ahead and simulate this again. Okay, so I've got an error in the dimensions. Okay. Oh, you know what? That is tank dynamics coming out. I just want to get the measured level. I have the 2 tank values. I just need to bring out 1. Okay. So this was outputting both tank 1 and tank 2. Here's tank 1 coming out, and then tank 2 coming out. I'll actually bring it right off of this signal. They said I had 2 signals coming into that summation when I was only looking for 1. Okay, so I just want to get the second tank, and I split that. This is a mux and a demux that splits the signal from 2 signals right here to 2 individual signals, and I'm just bringing out the second tank. Okay, so let me go back here and I'll run this again. Okay, so my target value is 0.5, and you can see that the red is my target. And let me just get my another diagram up here, my measured levels. Okay, so you can see tank 1 and tank 2 as they're progressing. Okay, and you can hit rescale right here. Okay, so I'm trying to get this purple line up to 0.5, and we're going to see how well it does it with this controller. Okay, so you can see that the yellow line, that's tank 1, that's going to head up a little bit higher. Okay, and then tank 2, I'm trying to get that up to 0.5 eventually, with this tuning. Okay, so so it's about 37% of the way through. You can monitor the progress here in terms of the simulation time. You can change the total simulation time up here before you click run. Okay, so that's another thing that you can do. And then you can also monitor this through this diagram right here. Okay, so you can see that tank 2 is approaching that set point. The controller is adjusting this pump output for us instead of us doing it manually. Okay, and so I have let's say a disturbance that comes along. Let's say I change, or let's say I just change my set point. Okay, so let's change it down to 0.39, or I'll just do it to 0.4. Okay, and then I can come back and see my new set point, and you can see this tank 2 level dropping. And in this case, it's the PID controller that's adjusting the pump output that is feeding into the top tank to adjust and maintain this level in tank 2. Okay, so that is just a summary of this problem. We designed a controller based off a first order plus dead time approximation to our model, and designed this controller to maintain a level in tank 2, and did this with a Simulink block. Okay, so I'm just going to, at the end, let me go ahead and just make this a little bit bigger. Again, the blue is actually the set point. I'll go ahead and fix that. And then the red is the response, how the controller did. And so you can see it made it up to the set point, and then as I dropped the set point, it also dropped to try to match that level. Okay, and then you can also see, for example, the pump output, what the pump was doing as being controlled by this controller.